So this is EE698G, lecture 6. So let's quickly recap the SR latch based PD. So we constructed an SR latch based on 2 NOR gates. It can be done by NAND gate 1 also. And then you should be able to configure it to act as a PD. It was one of the questions I thought I should give you for an exam. I came prepared So just to give you the questions that I had in mind, which I did not put for this particular exam. For example, we dealt with the XOR-based PD, right? What if it was XNOR, right? Then what would be the characteristics? Whether it can act as a PD, etc., would be one question. Now, let's say I took a XOR-based PD. Let's say this was in one. What if I connected a small delay element? Let's say this element was offering a delay of 10 picosecond and into was here. Then how would the characteristic of this PD change? Right. So this was another question I had in mind. Then the SR latch based PD. So here, change the supply instead of from 0 to VDD. What if the supply went from minus VDD to plus VDD? What if instead of NOR based SR latch, it was a NAND based SR latch? Now, on top of this, what if you had a delay element, much like this? So if this was your SR latch based PD, what if you had some delay element here? What if I had delay elements in both the paths where they had different delays? So with all of this, you would be able to derive a VPD average versus phase error characteristic. Right? So basically in this topic, there are a lot of possible interesting combinations that can come as questions. So your focus should be on understanding how to get to the characteristic, the method that is being followed. It is okay even if you don't remember the results for each PD by heart. You can always derive it. Okay. So we have our SR latch based PD. This was the reset pin. Corresponding to that, we got the up signal. This was the set pin. Corresponding to this, we got the down signal. And we connected in one to the set and into to reset. So again, an interesting question would be, what if I reverse the connection? In one went to reset and into went to set. How would it change the characteristic, right? So what was the truth table that we derived? When both of them are 0, this is hold. 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1. This gives you 0, 0, right? Now, based on this, we derived for 2 cases. So case 1 was when the phi error was greater than 0, right? But of course, this should have some limit. We don't know what that limit is yet. So we would have derived it for phi error varying from 0 to some value. We don't know what that is yet. That's okay. Now, what is the expression you got for VPD average? Please look at your notes and tell me the expression. VDD by 2 into pi error by pi minus 1, right? Now we solved for one more case where the phase error was lesser than 0. Again, there would be a limit during which this equation is valid. So this would mean that phase error is lesser than 0 and phase error is greater than some value. Again, we have not figured out what that value is. What is the expression for VPD average? VDD by 2, 1 minus mod of phi error by pi, right? Now, for finding this scenario, one quick thing that you can do is look at the waveforms you have drawn for that case. So this is the waveform that you sketched for the scenario, right? Now imagine pulling your into to the right side, which means, yeah, it is getting recorded. Screen is shared and it is getting recorded. Yeah. So now imagine you are pulling into to the right side, which means your delta t is now going to progressively increase. So corresponding to that, if the same set of equation is being valid, when your delta t is increasing, you would expect the width of up to increase. And you would expect the width of down to remain constant. So now imagine pulling this into to this side. At what point do you think that behavior of up and down is going to change? After pi is your guess, right? Which means somewhere around this point. You think when delta t crosses this point, it's possible that the behavior can change. And that's a very decent guess. So now that we have a guess, let's write it down and see if that is the actual scenario. So now let me consider a case 3. Where phi error is greater than pi by a small amount. Okay. So now you have to sketch in one, into, up, and down corresponding to this case, and estimate what is the BPD average you get. Please try. Let's say this is my in1. I've sketched my in2. So let's start plotting up from this point. So S is 1, R is 0. What is the output? This 1. So it remains still 1 till here. Right? What about down? Last row there. What about down? Look at the SR latch truth table that you have written, right? So go back to your notes from previous class. You have the SR latch truth table. If your S is 1, so I'm looking at this point, S is 1 and R is 0, what is up? Up is 1, down is 0. So again, the last row there, what happens after this point? So your S is 0, R is also 0. It has to hold, so no change. Right? So the last row here, last 2 rows here, can you comment on what the signal should be after this point? What should happen to up? Yeah, it goes to 0. So it remains at 0 till this point, and down goes. What happens after this point? Both come to 0. Right? So now again, S is 1 and R is 0. So it goes high. Now it has to retain the previous state. So it retains the previous state. Then this gets reset. And then because both of them are now at 1, it has to go down to 0. Okay. So if I look at this, I see that this forms one period. Right? If you're not very sure about this, you can draw for more cycles and you'll see that this is the period that is getting repeated. Okay. Now I have to identify what is the average value of up. So what is this value? T0 by 2 because it corresponds to this. right? So this is T naught by 2. What is the distance from here to here? That is T naught, right? What comment can you make about this pulse width? Is it T naught minus, so which is bigger, T naught or delta T? T naught is bigger, right? So this is T naught minus delta T. Is that clear to everyone? Can you see that this has to be delta T? So this is measured from the rising edge of the signal to the rising edge of the signal. That means this has to be delta T. So if this is T naught and if this distance is delta T, then the remaining pulse width has to be T naught minus delta T. Any questions on that? Okay, so now if that is clear, my average VPD is average value of up minus down. What is the average value of up? So this is VDD by 2 minus average value of down is T naught minus delta T into VDD by T naught. Okay, any questions on how I've written the equation? Okay. So this is VDD by 2 minus T naught by T naught gives you 1 minus you have delta T by T naught. Delta T by T naught I can replace as phase error divided by 2 pi. So this into VDD. So this is equal to, so you have VDD by 2 minus VDD. Right? So that gives you minus VDD by 2 plus phase error by 2 pi into VDD. So I take the VDD out and the expression is phase error by 2 pi minus 1. Take 2 components. Sorry, 2 is common. Phase error by pi minus 1. So this is the same expression that you got when phase error was greater than 0, right? So looks like the expression is valid beyond pi also. Now again, you imagine pulling this into signal to the right. Where do you think is the next point we want to check? 2 pi? Yeah. So you can do this calculation yourself. It turns out this particular equation is valid only from 0 to 2 pi. So now if I sketch this, after 2 pi, that it is just a loop. Right. What happens after 2 pi? It will be same as phi error greater than 0. Okay. Okay. So this is phase error. This is VPD average. So when phase error was equal to 0, what is the value you get? Is it plus VDD by 2 or minus VDD by 2? Minus VDD by 2, right? When phase error is equal to pi, what do you expect? 0. And for 2 pi, so you will have the same plot. Right? Now you can also plot this on the other side. Again, if you have a doubt, simply take a sample case, sketch for the waveform, and then imagine that waveform being pulled to left or right. So you will see that this is also like this, right? And beyond 2 pi, you would again expect the curve to repeat. Okay. So this way you can sketch the characteristics of a phase detector for any possible input combination of phase error that you choose. Take a phase detector, you sketch out maybe for phi error greater than 0, sketch the waveform. Now imagine the waveform being pulled to left, right, and see how your output is going to vary. So what is the monotonic range for this? So you can either choose from 0 to 2 pi or from minus 2 pi to 0, but the range is at 2 pi now. So the problem is, as long as you don't operate, let's say from minus pi to pi, then you are okay. Right? Between minus pi to pi, when you hit 0, your gain suddenly can go from minus VDD by 2. Your direction can change. If you are moving from some point here to here, for small variations here, your VPD average is increasing, right? But let's say you were increasing, and then suddenly it will drop to a much smaller value, right? There is a discontinuity and a sharp discontinuity where the value difference is very large, right? You have a VDD difference. So you would prefer to not have any discontinuities like this when you're operating. Okay. So now, what do you think will happen if I chose both input signals with different duty cycles? Do you think it will cause a problem? It will change the characteristics, right? So now it looks like our phase detector characteristics are being a function of the duty cycle of two signals. Now, let's say I want to get rid of this duty cycle dependency, right? Which means my phase detector should only be a function of one of the edges. And if you are measuring delta between the rising edges, it should only operate on the rising edge, right? So then this line of thought, what is the first element that comes to your mind when I started saying it should be flip-flop, right? So now you can also build phase detectors using flip-flop. Now let me introduce you to a particular type of phase detector called as phase frequency detector. This is PFD in short. This is also called as a three-state PFD. So the significance of the second term we'll see in a little while, but let's focus on the structure of this, right? Now you can see that we also have frequency detection in the name. That is because it can give you a measure of the frequency difference as well. It is not relevant to us right now because for now we are assuming both in1 and in2 have the same frequency. So in future, there are other loops where frequency generation is also involved. Right now, our frequencies in the loop are all the same. We are only focusing on phase or delay generation. Later, we will see loops where a frequency generation is also involved, which would mean that the frequencies you are comparing are also different. Now, in such cases, your PFD can give you some measure of the frequency difference as well. Right? But for now, we are interested only in the phase detection properties of the PFD. So as you rightly imagined, there is going to be a flip-flop involved. Okay. Let's say I connect the D input to VDD, is connected to 1 at all times, and I give in1 as the clock signal. Right. Similarly, I take one more flop and I give in2 as the clock signal. And this is my up, this is my down, right? So now you can imagine that both up and down are going to be sensitive only to rising edges in in1 and in2. Do you see any problem with this arrangement? You have up and down. Right. Correct. So the moment your first rising edge of in1 comes, up will go to 1. Right? For every other rising edge, you are simply going to sample 1. So it will go high once and stay there. Same problem with in2 also. So we need a mechanism to reset it. So how we reset it is as follows. We take up and down. And whenever both up and down become 1, so this situation you can detect using an AND gate, you will come back and reset both the signals. Okay. Now let us also assume that this AND gate has a delay given by T reset. Right? So this delay is essential for us to plot the waveforms, which is why I'm putting it here. you can assume that rest of the modules do not have any delay associated with it. So let us do the same procedure again. Let's assume two cases. Case one, where phase error is a small positive number. You will have to plot, this is your reset signal. Sketch in one, into, up, down, and reset. Once you are done with this, do for phase error slightly lesser than 0. So your up signal is going to go high with the rising edge of in1. With the rising edge of in2, the down signal will also go high. Now, when both the signals go high, reset will also go high, but we have assumed a delay of T reset for the AND gate. So it will go high after a T reset delay. Once the reset goes high, your up is going to come down, down is going to come down. And once up and down have come down, again after a T reset delay, this will come down. So what is the width of up? This is delta T plus T reset, where this is delta T for you. And the width of the down? This is T reset, right? So basically, if I do up minus down, it looks like I'll be able to extract this delta T information. Yes, you have a doubt? So the reset, let's say, you need to understand the waveforms, right? So I think it is a relevant question. So let's say up came down also came down. Your output will change T reset time after that. The delay from input to the output is T reset according to the figure. You can think of the AND gate output being ready after T reset. Right? Input changes, the output changes after T reset. Right. So the input has changed here. Now after T reset, the output is going to change corresponding to that. Okay. Now I can also plot the next period. So again, corresponding to rising edge in N1, my up will go high. Rising edge in2, down is going to go high. After a T reset delay, my reset will go high. So both of them will come down. And then again, after a T reset delay, reset will come down. So this is how your period is going to repeat. Now, it looks like what we should do is up minus down. Just to be sure, why don't you plot the case for phase error lesser than 0? But why don't you plot it? So did you sketch the waveform for the reverse case? Yeah. Did everyone sketch? Please try. So if you're finished, you can think about what the VPD average versus phase error curve will look like. Right. So again, at the rising edge of into, your down is going to go high. Rising edge of in1, up will go high. Once both of them go high, after a delay of t reset, your reset will go high, which means up and down are going to come down after that. And then the t reset will also come down after another reset delay. Down goes high here. Up goes high here. And they'll come down after a reset delay. Right? Now, in this case, the delta t information is now present in the down signal. Okay, so it looks like our original definition of VPD average being equal to up minus down average should still work fine. Can you tell me what expression you get? This will be equal to phi error into VDD by 2 pi. Is it clear how we got this? So in calculating up minus down, you can clearly see that this T reset portion is going to get cancelled. Right? So I can directly use the delta T portion for the calculation. So this will be equal to delta T into VDD divided by T naught. And delta T by T naught can be replaced as phase error by 2 pi. Okay. Similarly, what is the expression you get here for VPD average? So it will be, the expression would be again delta T, again up minus down is what we are doing. So you'll get minus of delta T by T naught into VDD. Delta T by T naught, you can replace it as phase error by 2 pi. But your phase error is negative. You have already accounted for that negative by putting the negative sign here. So to be correct, we put a mod sign around phase error. This is okay? Right. So now our aim is, of course, to plot VPD average versus phase error. So we know the characteristics of this PFD over a large range, right? So we repeat the exercise again. We imagine pulling into to this side. Up to what point do you think the equation is going to be valid? So I'm pulling into towards this side. This edge. So your delta T is going to increase. This edge of into is going to move like this, which means this delta T will also increase, right? The down signal's position alone will be shifted. Now, at what point do you think that behavior is going to break down? At 2 pi. 2 pi is a decent answer. Do you think anything will happen at pi? No. Why not? Right, we are using flip-flops that are getting triggered at positive edge. So the falling edge is not going to have any impact. Now, at till 2 pi, we are confident that this behavior is going to hold. Right? So let us take a scenario where the phase error is slightly greater than 2 pi. So this is where your phase error is greater than 2 pi. So why don't you sketch for this? After you have sketched for this, see if you are able to do VPD average versus phase error plot directly. Yeah.
Take it for 2 pi. Reset signal is delayed by T reset.
Yeah.
So if the T reset was initiated before the POSET and reaches reset after POSET, then would that newly sampled value?
So your question is if the reset value let's say
that reset signal.
The reset signal is
Okay.
happening
Yeah.
at this edge.
Okay. One of the posits comes in the middle of that reset icon.
Then it is going to miss it. Because by T reset, we generally prefer it to be a small value. Right? So this is a very good question, but let us consider for a case where pi error is greater than 2 pi. Let's sketch the whole plot and decide where we want to lock. Right? If the scenario you're talking about is coming very far away from our locking point, then it's very unlikely that it will happen. Right? So let us do this. You can help me when I'm doing the figures. Let's say this was in one. Into is delayed by more than a period. So your up signal is going to go high here, corresponding to the rising edge in N1. Where does the down signal go high? Corresponding to rising edge here. Right? Once they go high, after a reset delay, your reset will go high and it will come down after a reset delay. And the signal is going to look like this. Now let us again plot. It will again go high at this edge. Down is going to go high corresponding to the edge here. And then it will both come down after a reset delay. And you'll have the reset signal here. Let me plot for one more period. Up goes high here. Down is going to go high here. And after this, both of them will come down after a reset period. Right? So now if you look at it, it looks like the up and down signal has something happening over the first period, and then a totally different pattern is happening throughout after that. So if I'm observing this waveform for a long time and then taking the average value after it has achieved steady state, this is like a transient, right? So this will not affect the average if I observe it for a long time. So we are interested in the steady state average. So you take the average beyond this point. So let me consider one period after this. So let's say I consider one period like this. Our VPD average is up minus down average. What is the average of up in terms of delta T? So what is this? What is this pulse width? So what is this pulse width? This is T reset. Now I know that this is going to have some T reset plus something. Now I'm interested in what that something is. So we are looking at it in the time domain, right? So that will be equal to delta T minus T naught. Is that clear to everyone? Yeah.
How do you get to know that we are taking the time difference or the phase difference between the first edges or the second?
Yeah, same question that Akshay asked. So it's a very good question. You can also think about it, right? So then the up minus down average, again, T reset is present in both up and down. Therefore, the expression is going to be delta T minus T naught into VDD divided by T naught. So this gives you phase error by 2 pi minus 1 into VDD. Right? So looks like beyond 2 pi, the expression is changing. So now let us plot the VPD average versus phase error. right? So we are going to plot it till, let's say, pi, 2 pi, 3 pi, and 4 pi. On this side, minus pi, minus 2 pi. What is the curve that you got? Between 0 to pi, how would it look like? Straight line. From 0 to 2 pi, it will look like a straight line, right? Similarly, from 0 to minus 2 pi, it will be a straight line like this. Now from 2 pi to 4 pi, this is going to be your curve. Similarly, you can again try this as a homework. From minus 2 pi to minus 4 pi, your curve is going to look like this. Okay, so now the question that you have asked is, if I get a VPD average as some positive value, how do I know whether it is here or whether it is here, right? But how do I know whether it is this or this? Any guesses? We have to choose a region of operation, right? So you can't find out whether it is around pi or around 3 pi just based on the PFD output. So that is always a tricky part. But generally, when you put it in loop, you will adjust your region of operation such that you clearly know where it is going to come. But as such, the PFD alone cannot give you that information.
Like it may happen that the delay of that VCDL may cross 2T naught.
It can. But if you design your VCDL, so the VCDL...
The difference between the first edge and the second edge, there is difference between those two. It may happen it can cross 2T naught, then we will take the difference between the first, second edge and those things.
Correct. That is correct. But now the thing is the VCDL design is under your control, right? So when you get TP versus VC, you make sure that 2T naught is not even an option. It is beyond the VCDL characteristic. Then you are guaranteed that the VCDL can never give you 2T naught. Right? So then you sort of know that the delay you are getting should be around pi for a given value of VPD average. Okay. But there is a lot more nuance involved. Again, we are slowly going to learn about all of these small issues that will come into picture. So now the question that Kevin asked, so let me sketch the plot. Can you tell me the scenario where you expect this to happen? Let's say in1 is like this. How do you want your in2 to be?
On the very close to 2 pi phase difference.
Here is it? I don't think this. Then you will miss out on this edge. Is that the concern? So let's sketch up and down quickly. Up is going to go high here. Down is going to go high here. And the scenario that he's talking about is, so I'm not going to sketch a T reset. I'll simply assume that it is coming down after a T reset. Now, if this happens, where will up go high again? Up will go. So this edge has been missed. It has happened during the T reset, right? Down will go high before that. So up is going to go high here. Down is going to go high here, right? And then both of them will come down after a T reset. Again, up will come high here. And the down is going to come high here. And then both of them will come after a T reset. So your PFD is still giving you a phase error. It simply detects this as a negative phase error. So which means your characteristic is going to slightly shift. Yeah, I think you have mirror image part, no, but you had it. Okay. So is the waveform for the first up and down clear, right? So now they have come down, right? And we have completely missed this rising edge of up. So now where will up signal go high again? Corresponding to this edge. So up has gone high here. Down has gone high here, right? And your reset signal, so will go high a T reset time after both of them have gone high. So they will come down at that instant. Now again, your up will go high corresponding to this. Your down goes high corresponding to this. Okay? So it is still detecting something, just that your average value is going to be different from what you had expected. Okay? So now, let's say for a given value of T reset, you can check how your VPD average versus phi error characteristic is going to change. So you expected, ideally, if you are around 2 pi, you would have expected a value somewhere here, right? But instead, now you can clearly see it's going to be a negative value. Right? So there is some change in the characteristics. So what that changes, you can sketch it. Second edge of, so this is the first edge, second edge. Second edge of in1 and first edge of in2, correct. Instead of recognizing that in2 is lagging in1, your PFT is now incorrectly measuring it as in2 is leading in1. So these calculations are all very logical. Given any combination of inputs and any combination of PD, you should be able to sketch out the waveforms and determine what the average characteristic of the PD is. So now I mentioned that, so before I go on to the reason for three-state PFT, can you tell me the monotonic range where you would want to operate? Yeah. So you will want to operate from minus 2 pi to plus 2 pi, right? And this gives you a range of 4 pi, so the largest we have seen so far. And this is also linear within this range. So one interesting thing to notice in this particular PFT structure, whenever the phase error is positive, you are getting a positive output, right? Phase error is negative, you are getting a negative output. This was not the case with XOR-based PD and other PDs, right? You had it switching from positive to negative as well. So this is the property that becomes useful when we look at the frequency detection mechanism of this PFT. So that we'll deal a little later. Now, let me tell you why this is called as a three-state PFT. Any guesses? Three signals, right? Those are three signals. We are looking for some reason, three states, right? So you have up and down. I can tell you that up and down is what is determining the state of the PFT. For example, let's start with up and down being equal to 0, right? This is a very stable state. Now, if you had a rising edge in 1, what is the state you go to? Up is 1 and down is 0. Now, if I have a rising edge in 2, so this is in 1, in 2, you come back to up equal to 0, down equal to 0. You have a temporary state in between, but that is okay, right? The stable state is up equal to 0 and down equal to 0. Similarly, if you have a rising edge in 2, you go to up equal to 0 and down equal to 1. And you come back to this state when, rising edge of n1. So you have three stable states as output. Therefore, this is a three-state PFT. Okay. So now let me show you one very interesting phase detector. It's very interesting because of the simplicity of the implementation, right? So now we have taken two flops and build a phase detector. What if I try to implement a phase detector using a single flop, right? So I have only a single flop, D, clock, and output. I connect in1 here, and I connect in2 here, and I simply monitor the Q output, VPD. Right? So can you quickly sketch for two cases? Case 1, where phase error is greater than 0. Case 2, where phase error is lesser than 0. And then sketch the VPD average versus phase error. then you need VPD average versus phase error plot. This way. So we have in 1 and in 2. So in 2 is simply going to sample in 1. Right? So the VPD is going to be 0. At the first sample, it has sampled VDD. So it will go high here. Next sample is still VDD. And it remains high, right? So if I ignore the initial transients, then the VPD average will be equal to VDD. So now imagine pulling this into waveform to the right. For what value of delta t is this output going to change? Yeah, till pi or t naught by 2, it will remain as 1. After that, it will begin to sample 0. Now let's assume, is that clear? Up to t naught by 2. Now imagine pulling it further. Till what point will it be 0? Till t naught, right? Till 2 pi. After that, it will again become 1. Okay. So now what about phase error lesser than 0? Similar behavior, right? So I don't even have to sketch it. So we can directly plot the VPD average versus phase error here, right? So instead of calling it as 0 and VDD, I'll simply call it as V high and V low, just so that the curve is very clear, right? So between 0 to pi, what do you see? It will be at V high. Between pi to 2 pi, it will be at some V low. And then further on. V low is typically 0 and V high is typically VDD, right? Any other concerns with this plot? Now, if you're using such a plot, I mean, such a phase detector, where do you think the locking point would be? Sorry? Between pi to 2 pi? Depends on? It depends on those values, but given a property like this, where, so what will happen is you will try and lock to 0 point, because on an app, so every measurement, the loop is, let's say you measured a positive phase error, then the loop is going to try and do something so as to reduce the phase error, right? So then in the next couple of cycles, it will begin to measure negative phase error. So on an average, it is going to switch between positive phase error, negative phase error, etc. And you would design it such that it can still lock to 0. So it is possible to construct a delay lock loop, a locking loop using such a phase detector, even though the phase information is not linearly, or you don't have a, when the phase error is increasing, your VPD average is constant. It is not increasing. But even with this, it is possible to lock to a proper locking point. Okay. But do you think there is any usefulness for a phase detector like this? Or again, is it just an academic exercise?
For detecting whether one is lagging or leading. Yeah.
Correct. So if you are interested in a range between minus pi to pi, this is very useful in detecting whether the signal is leading or lagging. Right? Anything else? How would you measure the frequency? You will have to test the entire characteristic to measure the frequency, right? You are telling me because, so No, so good attempt, but I don't think you can measure the frequency using this. Yeah, you. So you'll have to change the phase error with risk. So instead of phase error, let's say you are sweeping the delta t, and then based on that, every point you measure the VPD average, and then you plot it and then find the frequency. Is that your attempt? No? What is? Correct. But so phase error, so because you're talking about frequency, let's say I directly talk in terms of delta t. All that you know is whether the delta t is greater than T0 by 2 or lesser than T0 by 2 in terms of half period. It doesn't tell you what is. So you'll have to sweep the delta t, find out for every delta t what is the value of the output, and then measure frequency, right? But there are easier ways to measure frequency than this, that's all. But technically you are correct. So with all the push of moving everything into digital, even the smaller analog modules these days are getting implemented in digital circuit, or at least part of it is becoming digital these days. So this is very easy to incorporate into the loop, right? So the output is a single bit, and you can simply do some processing on the single bit and then have the rest of the loop in digital. So that is one reason. The other reason is, of course, the implementation is so simple. It's just one flip-flop. So this DFF-based PD also has its uses, but in certain type of applications. It's not just an academic exercise. It's a useful circuit. Okay. So now, if I say that we are going to lock to t equal to 0, can you make any comments on the KPD at that point?
It was not defined.
But if you had to make a guess about the slope. So not defined, infinity, all of these are the answers, right? Now it turns out you can precisely define what is the slope of this curve, that is the gain of this phase detector, if you take into consideration certain practical non-idealities. And the non-ideality we are going to consider is the clock jitter. Let us take a quick look at that answer, right? So you're saying that if I consider the delay of the flip-flop, let's assume that I take a delay from clock to Q path, some TCQ, right? Which means after into has occurred, the output is happening after TCQ, right? Then all that it means is that instead of the output changing here, the output is going to appear here. You'll simply have a delay. So your curve is either going to get shifted to, so I think the curve is going to get shifted to right? It will shift to left. No, it will not remain same, right? So let's assume the delay between in1 and in2 is 0. Right? Now we are saying that the output is present after a TCQ delay. So it is going to measure this. Now, so it is going to shift left. Right? This will come here. So for example, let's say the phase error between them was slightly negative. Right? So because of TCQ, let's say even though the into is happening here, the actual sampling is happening somewhere here. So you are still going to measure VDD. Right? So it is going to shift depending on what the TCQ is. So now you can also think about some TDQ value. Right? So basically a setup time. If the in1 has changed before that setup time, then the correct value gets sampled, else the previous value gets sampled. So all of these you can consider. Right? So, but that is going to simply shift the curve left or right. So let me tell you a few things about jitter. So anytime you have a clock signal you're dealing with, it has jitter, right? So let's assume that this is the very ideal clock. And these are the edges at which you expect the right? These are the points at which you expect the rising edges to occur. Now, if there is jitter present in the system, these edges are going to shift around the ideal position by a small amount. So instead of having a rising edge here, it might rise here, or it might have a delayed rise. Similarly, it's possible that the second edge is occurring a little late. Maybe the third edge is occurring a little early, etc. Now I'm going to represent these as Tj0, Tj1, Tj2, etc. Now individually, these values can be positive or negative, meaning the shift from the ideal position could be such that the edge is delayed, or it could be such that the edge is leading than the expected ideal position. Now let's say the ideal period was equal to T0. In the presence of these jitter, can you tell me what the new period is going to be? So Tj1 minus Tj0, where individually they can be positive or negative. Okay, so if your clock edges are going to shift around the ideal position, you will also have your time periods varying from one clock period to the next. Okay, so now in the presence, so let me consider, so these signals, this jitter is not deterministic, meaning you cannot predict what their value is going to be. And that is because the jitter is occurring due to random events within the circuit. For example, if you have heard about noise in the transistors, such as thermal noise, flicker noise, etc. If you have not heard about it, don't worry yet. These are certain random processes happening in the circuits due to which jitter is occurring. Since they are random, jitter is also going to be random. So this means to study about jitter, now we will have to look at its statistics. So we talk about, yes.
Is it the shifting of those edges, or it is the transition time?
Shifting of the edges.
Not the rise time and fall time.
Not the rise time and fall time. So even if I consider a signal with some rise time, in the presence of jitter, this can rise a little later, or it could rise a little earlier. Very simplified diagram, but this is what has happened. Okay. So now if I consider, is there another question? Okay. If I consider an ideal clock edge, and I say that the edge can shift for some time around it, maybe it is occurring a little earlier or it is occurring a little late, I can represent this information using its probability distribution. So we would expect that the probability with which it is occurring at its ideal position must be higher, right? And the probability should decrease as you move further and further away from the ideal position. And this is in fact true. You get a Gaussian distribution with mu equal to 0. That is, we are looking at Tj now. So the jitter being 0 will have the highest probability. And as you move away from it, the probability is going to decrease. Now, if I have a signal with, let's say, a very small sigma, right? It means that the probability of the edge shifting around by large amounts is smaller, right? That means that the clock you are dealing with is relatively clean. Now, the opposite case is where you have a clock like this, which means the probability of finding an edge further away is still relatively higher compared to the earlier case, right? So this means that you are dealing with a clock which has more jitter than the earlier clock. So it's not a very clean clock. So now let us consider our scenario of this D-flip-flop based PD. So I'm simply going to assume that in1 is very clean. It doesn't have any jitter associated with it. And we will assume that the in2 edge now has some jitter associated with it. So let's say in1 and in2 were separated by delta t. Now the in2 edge has some jitter associated with it that I represent using the variable Tj, right? Now, what is the delay that is being measured by the PD? So at this edge, what is the delay? That is delta t plus Tj, right? So now what would the output be? Your VPD value is going to be the high value if delta T plus Tj is greater than 0. This is going to be a low value if delta T plus Tj is lesser than 0. So far, okay? Now let us write the expression for VPD average. Now, of course, this is again a matter of, it is a function of Tj, not just delta T. And you can talk about Tj only in terms of probability. So you will have to write your VPD average using probability distribution of Tj. So let's start by saying that VPD average can either be VH or it could be VL. So the average value will be equal to VH into probability that VPD is equal to VH plus VL into probability that VPD is equal to VL. So far, okay? So this is VH into, how can I rewrite this in terms of delta T plus Tj? Right. So this is delta T plus Tj greater than 0 plus VL into probability of delta T plus Tj lesser than 0. So now Tj is a variable that has a probability distribution, right? So let me represent it directly in terms of Tj. So this is VH into probability of Tj greater than minus delta T plus VL into probability of Tj lesser than minus delta T. So far, okay? Any questions from the back? Is it okay? Right. So let us look at the probability distribution and see if we can rewrite this in terms of delta T directly, because it becomes a little easier to plug it into simulation tools. This is integration, right? But I want to rewrite the equation in terms of delta T instead of minus delta T. That's all. So let's say, so correct, you have. So generally you would directly have a distribution of Tj, right? So you can either shift it using delta T plus Tj and then look for a result, or you rewrite it. And so let's do this and then you can ask your question at the end. Now let's say this is minus delta T and this is plus delta T. So when I say Tj greater than minus delta T, I am looking at the area under the curve as shown here. Right? Isn't this also same as the area under this curve? Huh. It's symmetric on both. Right? Similarly, the second constraint is Tj lesser than minus delta T. So that refers to this portion. Right? And that will be same as Tj greater than delta T. Okay. So I can substitute this. So this becomes V high into probability of Tj lesser than minus delta T. Sorry, Tj greater than minus delta T is this portion. So I can write it as Tj lesser than delta T plus VL into probability of Tj. Again, Tj is lesser than minus delta T. That is same as Tj greater than delta T. Okay. Now let me substitute the value for VH and VL. So let's say VH is equal to VDD. For now, I'm going to put VL equal to minus VDD. Right? You can put VL equal to 0 and still continue with the derivation. You will get a slightly different expression. So this becomes VDD into probability of Tj lesser than delta T minus VDD into probability of Tj greater than delta T. Do you think you can rewrite this? in terms of this, right? So it becomes 1 minus probability of Tj lesser than delta T. So this is now equal to VDD into twice of probability of Tj lesser than delta T minus 1. Okay, so we got an equation. Got an expression. What is the first step we have to do? Sanity check. Right. So let's assume that the jitter associated with the signal is 0, right? And let us say the delta T we are dealing with is positive. From the equation, what is the average value of VPD you get? So Tj is 0, delta T is positive, which means that this probability is always 1, right? So this will be equal to VDD. Now, if I assume delta T is negative, what do you get? You'll get minus VDD, right? So if I were looking at, so we had the phase error versus VPD average plotted. And what did you get around? So we have considered this for small values of delta T and small values of Tj, right? Tj equal to 0. So what do you see? You would have gotten VDD here and minus VDD here, right? And that matches with whatever the equation is telling us. So for Tj equal to 0, this simplifies to this scenario, okay? So it's already 6 o'clock. I'll deal with how we can make use of this equation in the next class. Thank you.